Do you like synthesis? Let's talk chemistry today. What if chemists could take the humble alkene and directly swap out one of its hydrogens with an alkyl group? That sounds straightforward, but for alkenes, it's been a surprisingly difficult challenge. Tobias Ritter's group proposed a new solution in an open-access 2026 Nature article: a decarboxylative alkylation of alkenes using carboxylic acids as the alkyl source. The really exciting part of this method is that it doesn't follow the usual radical playbook. Instead, it introduces a polar decarboxylative pathway built around an unexpected alkylzinc intermediate. Today, let's break down what they discovered, why it matters, and how it changes retrosynthetic thinking for alkene functionalization. Alkenes are everywhere, in pharmaceuticals, agrochemicals, detergents, polymers, natural products, you name it. But despite how common they are, directly alkylating an alkene CH bond is surprisingly difficult. Why? Because when alkenes react with electrophiles, their usual MO is addition across the double bond, not substitution of a vanillic hydrogen. That means there's no general alkene equivalent of a Friedel-Crafts alkylation for arenes. So if a chemist wants to convert a less substituted alkene for a more substituted one, that standard retrosynthetic shortcut doesn't really exist. Instead, chemists often have to build the alkene indirectly using Wittig reactions, Horner-Wadsworth-Emmons olefinations, Julia olefinations, or sometimes alkene cross-metathesis. These are all powerful, but each comes with limitations. Cross-metathesis, for example, can be highly substrate dependent, and many internal, cyclic, or highly substituted alkenes remain difficult or inaccessible. So the Ritter group asked a simple but deep question: can we directly alkylate alkenes using abundant feedstock alkenes and simple carboxylic acids? Their strategy combines two key ideas. Number one, turn the alkene into an alkenyl electrophile using thianthrenation. And number two, turn a carboxylic acid into an alkyl nucleophile equivalent through a redox-active ester and zinc reduction. These two activated partners are then joined in a palladium-catalyzed cross-coupling. So rather than forcing alkenes into their normal addition chemistry, the authors effectively create a workaround. They convert the alkene into something that behaves like a vinyl coupling partner, and the acid into something that behaves like an alkyl organometallic. That's the conceptual leap. The biggest mechanistic insight in this paper is that redox-active esters, under the right conditions, can generate a persistent alkylzinc species. It's pretty unusual. Most modern decarboxylative cross-coupling chemistry treats redox-active esters as radical precursors. You reduce the ester, carbon dioxide is lost, and an alkyl radical is formed. That radical then gets trapped in some transition metal catalytic cycle. But in this case, the authors realized radical coupling would be problematic. The alkene-derived partner, the alkenyl thianthrenium salt, can also participate in single electron chemistry. If both partners enter the reaction as transient radicals, then selective alkyl-alkenyl cross-coupling becomes very difficult. Instead, you get side reactions like hydrodecarboxylation and general reduction of the partners. And that's precisely what they observed under more conventional nickel and iron-based radical conditions. So they pivoted away from a radical coupling logic and toward a polar 2-electron pathway. Their proposal is zinc reduces the redox-active ester, but instead of only producing a fleeting alkyl radical that escapes into solution, the process ultimately generates a stabilized alkylzinc reagent in DMF. That alkylzinc intermediate can then undergo a far more controlled palladium-catalyzed cross-coupling with the alkenyl thianthrenium salt. That's the heart of the paper. Here's the basic sequence. Step 1. Alkene thianthrenation. The alkene is converted into an alkenyl thianthrenium salt. This is important because thianthrenation effectively transforms a simple alkene into a highly useful vinyl electrophile, often with strong control over alkene geometry. Step 2. Prepare the alkyl donor. A carboxylic acid is converted into a redox-active ester, typically an N-hydroxyphthalimide type derivative. Step number 3. Zinc reduction in DMF. When the redox-active ester is treated with zinc in DMF, the authors detect formation of an alkylzinc species. This does not happen productively in all solvents. In fact, DMF seems crucial for enabling or stabilizing the organozinc intermediate. Step number 4, palladium-catalyzed cross-coupling. Once the alkylzinc is formed, the palladium catalyst couples it with the alkenyl thianthrenium salt to give the alkylated alkene. So in simplified catalytic terms, palladium 0 undergoes oxidative addition into the alkenyl thianthrenium salt, the alkylzinc transmetallates, reductive elimination forms the new CsP2-CsP3 bond, and the result is a substituted alkene, often with high regio and diastereoselectivity. This is where the method becomes especially impressive. The paper shows alkylation across a broad range of alkene classes: terminal alkenes, internal alkenes, cyclic, monosubstituted, disubstituted, and even trisubstituted alkenes. That last category is particularly notable because highly substituted alkene synthesis is often difficult and unpredictable. The method also works with a broad set of alkyl fragments derived from carboxylic acids, including primary alkyl groups, secondary alkyl groups, strained rings, saturated heterocycles, and fragments from complex bioactive molecules. They even demonstrate late-stage modifications of fairly complex structures, including derivatives related to indomethacin, baclofen, 2,4-D, citronellol, carvone, paraldehyde, and rose oxide. That shows the method isn't just conceptually elegant, it also has synthetic reach. Another major strength is stereo control. Because the palladium-catalyzed cross-coupling proceeds stereo-specifically from the alkenyl thianthrenium salt, and because thianthrenation often gives predominantly one alkene geometry, the overall alkylation typically preserves excellent control over the alkene stereochemistry. Many examples are reported with very high E selectivity, often greater than 20:1. The authors also note previously developed Z-selective thianthrenation chemistry can be integrated, meaning both alkene geometries may be accessible depending on how the electrophile is prepared. That's a valuable feature for synthesis, since alkene geometry can strongly affect bioactivity and downstream transformations. The mechanistic section is one of the most interesting parts of the paper. The authors support the alkylzinc hypothesis in several ways. By NMR evidence, they observe signals consistent with formation of an alkylzinc species when the redox-active ester is treated with zinc in DMFD7. Mass spectrometry. Electrospray ionization mass spec detects species consistent with alkylzinc coordinated by two DMF molecules, supporting solvent-stabilized organozinc formation. Iodine trapping. When iodine is added after zinc reduction, they isolate the corresponding alkyl iodide in around 52% yield. That's a classic way to probe for organozinc intermediates. Independent organozinc experiment. They also prepare a related alkylzinc reagent independently from an alkyl iodide and show that it successfully enters the same palladium cross-coupling, delivering the product in good yield. Solvent dependence. In THF, they do not see comparable alkylzinc formation by NMR, reinforcing the idea that DMF is not just a solvent, but a key enabler of this chemistry. So while the pathway likely still begins with single electron transfer from zinc metal, the crucial difference is that the reactive carbon fragment is converted into a persistent organozinc intermediate, not simply left as a free radical to do uncontrolled chemistry. The method is exciting, but it's not without limitations. A few stand out. It currently works best with primary and secondary alkyl groups. Tertiary redox-active esters do not efficiently form productive organozinc intermediates. The process is two-step, since the alkene usually must first be converted into the alkenyl thianthrenium salt. Yields, while often good, are not universally high for all complex substrates, and the method relies on specific conditions, especially zinc in DMF. So this is not yet a universally direct alkylation of every alkene with every carboxylic acid, but as a platform, it's very promising. From a literature review perspective, this paper stands out for three reasons. First, it solves a long-standing synthetic problem. Direct substitution type alkylation of alkenes has lacked a general solution, especially for unactivated and more substituted alkene classes. Second, it expands decarboxylative cross-coupling logic. Most decarboxylative methods are framed through radical retrosynthesis. This paper introduces a polar decarboxylative disconnection where a carboxylic acid behaves as an alkyl anion equivalent after activation. Third, it reveals underused reactivity of redox-active esters. Instead of treating them only as radical precursors, The paper shows they can, under the right conditions, serve as precursors to organometallic nucleophiles. That's a potentially broader conceptual advance beyond the specific alkene alkylation. So to summarize, this Nature paper reports a regio- and diastereoselective CH alkylation of alkenes using carboxylic acids as alkyl sources. The strategy works by converting alkenes into alkenyl thianthrenium salts, converting acids into redox-active esters, reducing those esters with zinc and DMF to generate persistent alkylzinc intermediates, and coupling the two partners under palladium-catalyzed. The result is a new route to substituted alkenes across a wide range of alkene substitution partners, including challenging internal, cyclic, and tri-substituted systems. More broadly, the paper introduces a polar alternative to radical decarboxylative coupling, which could have implications far beyond this one reaction. If this concept continues to develop, it may become an important new chapter in decarboxylative cross-coupling and alkene synthesis. If you like this material and want to see more, please subscribe to the channel and click the like button. It really helps. Thanks for watching. Tune in next time.